Continuity. If f is differentiable at a, then f is continuous at a. Differentiable, it means you can find the derivative of the function at x equals a. F is continuous at a, that means you can find the function value, which is the same as the limit of the function as x approaches a, or the graph is smooth at x equals a. Consider this as a conditional statement P then Q. So the contrapositive, not Q then not P, would give the same true statement. Not Q, then not P, based on the P is the statement for F is differentiable at A, and Q as F is continuous at A. So not Q is F is not continuous at A, not P, F is not differentiable at A. When is a function not differentiable at a point? When f is not continuous at a, when f has a corner or cuts at a, when f has a vertical tangent at a. So different cases that would not make a, the point a at a function to be differentiable. In a graphical way, we can say when f is not continuous at a, in the case that we have to jump, so this case, f is not differentiable at a. The case that we have the vertical tangent, on the left side, the slope approaching negative infinity, the right side, the slope approaching positive infinity. So that means you have the vertical asymptote or vertical tangent at that point. Another case, the case that it has a jump or the hole. The jump means the left hand side limit not equal to the right hand side limit. And the hole means the limit does exist, but the function is defined at different points. The corner, that means it has the sudden change after you draw the graph, moving from the left, and then all of a sudden change the direction or doesn't have a smooth turn. Similar way, has a sharp turn. So all of these cases make the function not differentiable. In this example, consider the graph of G in the interval from -4 to +4. Part A, find the values of x at which the graph G is not continuous. From the graph, we can tell that x equals -2, we have to jump discontinuity. And also at the point 2, the graph is not connected. So x equals -2, x equals 2 would be the value of the x at G is not continuous. Part B, find the value of x at which G is not differentiable. If f is not continuous, f is not differentiable. So we just take the same 2 points that we obtained in part A. And also consider another case, the case where the graph has the sharp turn or it has the cut, like at the point x equals 0. That case, at that point x equals 0, the graph is not differentiable. So we add another point x equals 0. Notice that x equals 0, the graph continuous, but not differentiable. In part C, we're going to sketch the graph of the derivative of the G. Similar to the way that we sketched the graph earlier in this section, we have 1, 2, 3, 4 different pieces. The first piece between -4 and -2, the m is positive. It's positive and equals a constant term because you have the straight line, positive constant. And the next part is defined from -2 to 0. The m is less than 0 because the graph is falling down. But as x approaches -2, positive, the slope m approaching 0. For x approaches 0, negative, m is approaching negative sign but very steep down, so it's going to be negative infinity. The next portion between 0 and 2, m is positive because the graph is rising. We consider the point as x approaches 0, positive, the positive side, the m approaches positive infinity. For x approaches 2, negative, the m approaches 0. And in the last portion, between 2 and 4, m is negative, and also consider similar to the previous cases. So x approaches 2, positive, the m approaches 0. X approaches 4, negative, m approaches negative infinity. And then we put our information together to get the graph of the G prime. The location that m approaches either positive or negative infinity, we're gonna make it as a vertical asymptote. So at 0, at 2, and at 4. Now between -4 and -2, the slope is positive but equivalent to some constant. And don't worry about the scale, as long as we show it as a positive slope or the horizontal line with the value positive. And next part between -2 and 0. On the right side of -2, the slope approaches 0. On the left side of 0, the slope approaching negative infinity. Next part between 0 and 2. On the right side of 0, the slope is positive infinity or approaching positive infinity. And then the left side of 2, the slope approaches 0. Between 2 and 4, the right side of 2, the slope approaches 0. Just starting again right after you take off from the point x equals 2. And then as x approaches 4, negative, m or the slope is negative. So it's going to be below the x-axis and coming all the way down as the slope approaching negative infinity as x approaches 4 from the left. So we get the graph of the G prime.